So now we're going to start looking at reactions of alkenes. And given this is the first time that we've really started to study reactions, a few pieces of advice about studying here. Because ultimately you're going to be responsible for knowing all of these reactions. And two ways to approach this, and both of these are probably things that you'll want to do. First of all, you've got to know your mechanisms. That's usually the harder part. That's what's going to take the most time, especially early on. But also, you're going to want to be able to look at a reaction. For example, if we put that down as a reaction, and the question was to predict the product, that's something you're going to want to be able to do very quickly. If you've looked at any of the old exams for this part of the course, or if you haven't, one of the things that you'll see is that in this part of the course, most of the exams will have a page, maybe 2 pages of questions, just starting material, reagent, fill in the product. So when I took this course, the way I approached it was I made flashcards. And the way I made those flashcards was so, as we'll learn in a few minutes, the correct answer to this reaction would be this. So what I would put on the front of the card was the starting material and the reagents. And then, so that's the front of the card. And on the back of the card, I put the product. And over the course of Organic 1 and Organic 2, the stack of flashcards just got bigger and bigger and bigger. And then it became the kind of thing that, in addition to the normal studying I was doing, just a couple times a day I'd pull out my stack of flashcards, and 5 or 10 minutes you can just go through them. Now, 2 other caveats that if you are going to do something like this. Number 1, make sure you shuffle your pile every so often. Otherwise, you may just memorize the answers in order, and that won't help you when you get to an exam. Second thing is, every so often, start with the product side of the flashcard and say, all right, here's the product. How do I go backwards? What are the starting materials? What's the reagent that I need to make this product? Why do we do that? Well, we do that because when we get into synthesis in Organic 2, you're going to need that ability to go in both directions. So let's start with our first reaction, which we already saw a little bit of a preview of in the last chapter, but that's the addition of HX, where X is a halogen. So we did a very simple example of this in the mechanisms chapter, and we saw that the reaction is the alkene is our nucleophile, and it attacks the hydrogen, which kicks out the bromine. The result of this first step is that we've added a hydrogen at one of the carbons and form a carbocation at the other side. And then the resulting bromide anion attacks the carbocation to give us our product. So overall, what this reaction does is we add a hydrogen on one carbon and a bromine on the other carbon of what was the alkene. All right, let's make this reaction a little more complicated. But what's the product here? Well, what makes this one more complicated is the alkene is no longer symmetric. So we have two possible products. We could put the hydrogen on the middle carbon and the bromine over here, or we can put the bromine on the middle carbon. So is there a preference? Will we get one product preferentially over the other? Or will we just get a mixture? Will it be random? Well, this becomes a good case of let's look at the mechanism, because it's the mechanism that will help us to answer that. Of course, there's only one truly foolproof way to answer that question. What would that foolproof method be? Right, the one foolproof method is to go into the lab and actually run the reaction. But we know that the first step is that the alkene attacks the hydrogen, and that causes the hydrogen-bromine bond to break. So let's see where that takes us. Well, if it puts the hydrogen on the center carbon, we get the carbocation over on the side. Or we could get the opposite. The hydrogen adds on the end, and we get a carbocation in the middle. Is one of those better than the other? The answer is yes. The one on the right is better. Why is this one better? Well, this is a secondary cation, whereas this one's a tertiary. And so in many cases, if we have a more stable intermediate, such as the secondary cation, that means that intermediate's going to form more easily. And so now the bromine will attack the secondary carbocation, and we get this product, the one on the right, as our major product. And that's going to be true for any time you add HX, which could be HBr, hydrochloric acid, etc., to an alkene. You're going to get preference for the halogen being on the more substituted carbon. So two definitions that we want to add in. One is the term regiospecific, because this reaction fits under this definition. It's a reaction where two or more constitutional isomers can be formed. But one is favored. And again, we can see why based on the mechanism. We can also define what is known as Markovnikov's rule. So Markovnikov's rule is something that applies to alkene addition reactions and says the following. So Markovnikov's rule, as we've written it out here, basically says that if we're adding HX, and while this is most common to halogens, we'll see that this also applies to things like water and other reactions. If we're adding HX to an alkene, the hydrogen will add to the less substituted carbon, and the X group, which for the reaction we just looked at, which is the halogen, will add to the more substituted carbon. Why is that? Well, it's because of what we saw with the mechanism earlier, that it's the more stable carbocation. Right. Now, how do we know that this is the mechanism for this reaction? So mechanisms are another one of those things that we can never 100% prove. You can't actually see these electrons moving and the bonds forming and breaking. But in fact, studying the mechanisms of organic reactions, that's a whole field in and of itself. And while for most reactions, we won't really talk about how we can prove it, every once in a while there are some stories that we can definitely understand and talk about. The reason we don't normally get into it is just a time constraint issue, as well as the fact that some of the experiments that are used to prove mechanisms are extremely complicated. But as I said, you can never truly, 100% prove a mechanism. And one of the ways that we can see that is to look at a reaction known as the Wittig reaction. So the Wittig reaction is a reaction that we will study in Organic 2. And I would like to bring a couple things up. So why this reaction as opposed to other reactions? Well, as you're going to see, this reaction, there are some, it's not necessarily 100% proven what the mechanism is. So if we look in our textbook, and just for reference, this is the 6th edition of Smith. If you're watching this video in 2020, then that is almost definitely the textbook that we're using. But if you're watching this video in a future year, that may or may not be the textbook that we're using at that point. But if you go look the Wittig reaction up in Smith, and you'll find this in chapter 18. You'll find the following. But what if we look this up somewhere else? And just for convenience, for ease, I went and looked this up on Wikipedia. So the first entry This is from Smith, 6th edition. Second entry is from Wikipedia. But there are many textbooks that would match this second mechanism. And while you probably don't understand what's going on yet, the key point is, and this is the piece that's pretty easy to see, the mechanism that's in our textbook is clearly 2 steps. But this other mechanism, you can actually see is more steps. Why is that? Well, this is a mechanism that's still being studied. The mechanism that's in our textbook is the one that's most likely to be correct. But it's not 100% certain. And so mechanisms are, theories. We can always come up with more evidence to support a mechanism, but we can never 100% prove a mechanism. But let's just talk briefly about this HX edition and some of the things that we do know about it. So how do we know it goes through a carbocation intermediate? Well, we've got to go back almost 100 years now. And we're going to talk about Frank Whitmore. And it's always interesting to bring up Frank Whitmore, because here's a picture from Penn State of Whitmore Lab. And the significance to me for Whitmore Lab is that up here on the 2nd floor, when I started grad school, that was where I taught as a TA. So that was Whitmore. What did Whitmore do? Well, Whitmore did the following experiment. Took this alkene and added HCl to it. Now, if this reaction follows Markovnikov's rule, then we know that the chlorine will end up on the more substituted carbon. And so Whitmore did the experiment. And this was about half the product. What was the other product? It didn't put the chlorine out here. It actually put it at this carbon. It's not really expected because that carbon, where the chlorine ended up, isn't part of the alkene. So what happened? How did the chlorine end up in such an unusual spot? Well, let's look at the mechanism. Starts out how we would expect. Gives us the secondary carbocation. If the chlorine then attacks the secondary carbocation, we get the product that we expect. But it's only through the carbocation that the second possible answer makes sense. Because this product that was the unexpected one would come from a more stable tertiary carbocation. Is it possible to get from the secondary cation to the tertiary? Well, if this hydrogen was able to shift over one carbon, we'd get to a more stable tertiary carbocation. These types of hydride shifts, because we'd call this a hydride shift because it's not only the hydrogen moving, but it's bringing its electrons with it. So it's H minus that's moving over one carbon. These hydride shifts are not terribly common, but there's actually quite a bit of evidence out there for them. And so if that hydride was able to shift over one carbon, and if these occur, that's usually what they are, is a one carbon shift. It won't go halfway across the molecule to give a more stable carbocation. But in this case, if this hydride is able to shift over one carbon, we go from a secondary carbocation to a more stable tertiary carbocation. And so over the years, there's been a lot of experimentation done, and this carbocation mechanism is the best explanation for all of the information, all of the data that's been collected about this experiment.